Okay, we can get started. All right, time to get started. So, 3:07. All right. Okay, so I guess I'll start by just looking at the schedule for this week. This is week 2, and there's some reading. Remember, the reading is mandatory. Okay, so we've got the textbook, 6.1 through 6.5. That's just about Boolean stuff. Shouldn't be too hard. It's pretty much things I talked about last week. And then chapter 10 is about lists, I believe, and so we'll be talking about that later in the week. And I've got this supplementary reading on natural numbers, and there's kind of a funny story about that because I wanted to use a few pages from an old book by Stephen Cole Cleany, which, I suppose I should mention that, I mentioned that, Alan Turing's PhD advisor was Alonzo Church, but Alonzo Church had another PhD student who was Cleany, who was a famous logician, and no slouch in his own right. And, if you've ever used regular expressions, you've probably seen the little star thing. It's called the Cleany star. It's named after him. Anyway, so he had an old textbook where he talks about the natural numbers, and I wanted to give that to you guys. And I looked up who holds the copyright on that textbook, and it's, I don't know, maybe I shouldn't say this, but it's some politician guy who's very interesting. But so I emailed him, and he gave me permission, so I put that stuff on Blackboard. Okay, it's just a few pages, and it's supplementary, totally optional. Don't have to read it. But the plan is for today to look at natural numbers and to revisit this idea of mathematical induction, which should be, I hope, review for you guys. Okay, maybe it's been a while, I don't know. Okay, but before we get started, I also want to mention I updated the style guide. Where is it? Oh, here's where the natural numbers thing is. I could bring that up. So here, this stuff about the natural numbers, and there's just a few pages. Anyway, right, the style guide. Okay, let me bring it up. It's mostly the same, but I added a couple things here. Okay, that your program should always be well typed, so they should always pass the type checker. Never submit a program that doesn't pass the type checker. And when you're developing your code, you should be using the type checker anyway. Okay, so we're going to be a little bit more lenient on PA0. So if your program doesn't pass the static type checker, that's okay for PA0 because, I didn't say this already, but in the future you will lose points if your program doesn't type check because, that's like submitting a program that doesn't compile. Okay, and then there's some other some expressions are kind of redundant. Like if you have a Boolean, then there's no sense in saying B equals true because B is already a Boolean expression that is true if and only if this expression is true. So, stuff like that, just try to avoid it. But that's it, okay? So, let's see, I don't know how long this is going to go on today, but it's pretty neat. So I want to talk about the natural numbers. Okay, now, I haven't used this thing very much, so let's see. The natural numbers. Okay, which we can denote using a fancy little n like that. Okay. So what are the natural numbers? I'm sure you've seen them before. Here's some example natural numbers. Now, this first part is a little controversial sometimes. I'm going to start them with 0. Okay, 0 is the first natural number, and then 1, and then 2, 3, and so on to infinity. Okay, there are infinitely many natural numbers, and so I'm pretty sure that you've seen the natural numbers before. Okay, and so sometimes if you go over to the math department and ask some of them, they might insist to you that the natural numbers start with 1 instead of 0. But we're computer scientists, and we're not the only ones. I think if you ask the set theorists, they'll start at 0 as well. Okay, and someone let him. And I think there are actually faculty even within the CS department, who will tell you that the natural numbers start with 1. But we're going to do 0, okay? Right, so I can give you a definition. I can give you what's called an inductive definition of what the natural numbers are. And so we're going to start with what's called the base clause. Okay, so I'm going to tell you the natural numbers are defined by the following clauses. 1, 0 is a natural number. So I'm going to write it like this. The 0 is a natural number. Okay. Write it a little nicer. Okay. That's the base clause. Okay. And then there's the inductive clause, which I will write something like this. Okay. I'll say, okay, for any natural number, for any n of type nat, is another way of saying that, something called the successor of n is a natural number. Okay? So it's sort of arbitrary how I'm choosing to present this, but this is one way of doing it. Okay? So this is called the base clause, and this is the inductive clause. And then there's a third clause that sometimes gets left out, but I'll include it. Okay? It says the only natural numbers are those, I'll say, generated from 1 and 2. Okay, these are the only way. These two clauses are the only ways to get a natural number. So there are no other natural numbers except those that are 0 or the successor of another natural number. Okay, so this is just sort of a way of like closing off the definition, so that there's no one can come along and introduce new ways of generating natural numbers. Yeah.
What do you mean by successor?
So the successor is like +1.
Oh.
It's like so yeah, we'll see some examples, I guess, of natural numbers. But so basically, a natural number is something that can be generated by starting from 0 and then adding 1 some number of times, by taking the successor some number of times. Okay. So yeah, let's look at some example natural numbers. Whoops. Okay. Lost my cursor here. Here it is. So 0 is a natural number. Okay. The successor of 0 is a natural number, and that's, we would call that 1. Okay. And the successor of the successor of 0, which I could put parentheses here if we want. Okay. We would call that 2. So what this is just a kind of really simple unary encoding of the natural numbers. It's not particularly efficient, okay? Usually we would use like a binary encoding instead. That's what we use in our computers most of the time. But this is the kind of most fundamental presentation of the natural numbers by an inductive definition, okay? Right, and just for completeness sake, this third clause is called the extremal clause, but whatever. So that gets left out sometimes. Right. And so then, but it's only because of the extremal clause that we get to do mathematical induction. But you could do it the other way around, where sometimes people will, instead of having this clause, they'll say you can do induction as like a clause. It's kind of the equivalent, but that's not super important. But okay, so let's look at mathematical induction. Okay, so this is one of the nice things about natural numbers. Yeah?
If we've got 0, then what are the whole numbers according to this?
You mean, what do you mean by whole numbers? Do you mean like non-zero naturals?
I guess so, yeah.
It would just be, you could just leave 0 out if you wanted. I mean,
So then the whole numbers would be
Sure. If that's the way that you want to define them. I mean, sometimes people say whole numbers just as another term for natural numbers, and maybe they're including 0.
Okay.
But yeah, if you don't want to include 0, you don't have to. But that's what we're doing here. Yeah. So, but the important thing here is that with the natural numbers, they come with this proof principle called the principle of mathematical induction. Okay. So, mathematical induction. Whoops. Okay, and it goes like this. So suppose P is a property of natural numbers. Okay, so what that means is that if n is a natural number, then P of n is a proposition that is either true or false, right? Then we can say the following. If 1, P of 0 holds, so if 0 has the property, and 2, the following, write it like this, if for all natural numbers n, P of n implies P of s of n, the successor of n. Okay? If these two things are true, then we can conclude for all natural numbers P of n. Okay? This is the principle of mathematical induction. You can see it follows the structure of the definition of the natural numbers. So the idea is that you've got some property and you want to show that it holds for all natural numbers. And so that's sort of an infinite thing that you're doing, right? You could check for 0, you could check the property for some numbers, but you can never check all of them. So we have this tool for doing universal proofs over natural numbers that is induction. Okay, and you can break it down into these two pieces where you show that it holds in the base case, and then you have the inductive case where you get to assume the induction hypothesis on some n and then show that under that assumption you can prove that it holds for the successor of n. Okay, so I'm pretty sure you've seen this before. Is that true? Yes? Okay. Right. So I mean, if you look, it's kind of cool. It's almost like writing a little program for doing the proof, right? Or it's a little program that if you give it any natural number, it can construct the proof for that particular number by starting from 0 and then passing it through this inductive case n times. So that's pretty neat. Okay, and so I guess, right. I was thinking of doing an example. It's 20 minutes. Okay, so probably what you've seen. I forget how to add a new page. Insert page, that's fine. Or, okay. So probably what you've seen was something like this. Suppose you want to prove that for all natural numbers, the following is true. That if you take the sum from k equals 0 to n, okay, that is equal to n times n plus 1. Oops. Over 2. This is that triangular number thing where this is taking the sum of well, that sum on the left is, computing the nth triangular number, and then on the right there's a closed form formula for computing it instead of doing a sum. Okay, we looked at a sort of geometric proof of this fact, and then perhaps you've seen that there's a proof by induction as well, so we could step through that. Now, of course, I haven't precisely defined these things. I'm assuming that you know what the sum is, and that we have addition and multiplication defined and that sort of thing. I'm not going into that level of detail. Okay. Right. So how would you do this? You would say, okay, proof by induction. Okay. Base case. So I suppose I could write base case, which is when n is 0. Then you have to check that it's true when n is 0. So what's the sum when n is 0? Well, that's equal to 0. And what's n plus 1? Well, 0 times 0 plus 1 over 2. That's equal to 0 as well. So we're good in the base case, right? And then the inductive case, which is where you have, I'll write it as n plus 1 here, just to make it a little bit easier. But then, the successor case. So in this case, we get to assume an induction hypothesis. So I'll write IH. So we get to assume that this is true for n. And then what we need to show is that from that assumption, we can show that it's true for n plus 1. Ends up being like this, right? So I imagine that you've seen this proof before. Okay. And so how will I do it? Let's see, I'll start from this left side here and just try to turn it into the right side somehow by doing some algebraic manipulation and stuff. So let's go ahead and start with this. Okay, and right away, I'll show you something here. Of course, if you've seen this before, then you already know this thing will be equal to the sum up to n plus n plus 1, right? Because it's just a sum. So we can kind of take the last term and separate it from the others. Okay? Okay, and then by the induction hypothesis, this whole thing, whoops. Remember, our induction hypothesis is this. So we can rewrite this thing here. Okay, so it becomes n plus 1 over 2. Sorry, my handwriting, not the best. Plus n plus 1. And then there's a little bit more manipulation here. We could take this term and multiply it by 2 to combine it with this one. And I guess I'll write out the steps. Plus 2 n plus 1 over 2. And then you can factor out the n plus 1 to get and that was the thing that we wanted. So that's good too. So then we've done the base case and we've done the induction case. And so we're done. Okay? We've proved this fact that it holds for all natural numbers. Okay. So I just figured I could run through that example pretty quickly. So this is kind of a standard example. Okay. So now you might start to wonder why we're looking at the natural numbers. So, because there's a quote in that reading. Well, there's a famous quote by Kronecker who said something like, "God created the natural numbers. Everything else is the work of man." Right. So the idea is that the natural numbers are sort of primitive in a way, or they're called the natural numbers. There's a sense in which they're sort of from nature, right? They've been given to us. That they're not an arbitrary creation of humans. Okay. And there's also the sense that there's no sense in trying to understand the natural numbers in terms of reduction to something more primitive. That they are sort of just there, taken for granted, right? There's something kind of mystical about the natural numbers. But what we'll see is that they actually are. We can understand the natural numbers in terms of something that is more general, at least. Okay, so I suppose I'll start by showing you how that we can encode the natural numbers in Pirate. All right. Now, if I can find, I suppose I'll use code.pirate. Right. Zoom in a bit. Okay. So it turns out we can use the data type mechanism in Pirate to create a data type for the natural numbers. So I'll show you this. They say don't do live coding, but it should be okay. Okay, and I'll call it nat. Data nat. Okay, and so if you recall from our recursive definition, what's a natural number? Well, it's either 0, which I'll use a capital O, or successor of another natural number. Okay, so this is probably the first time that we've seen a recursive data type, because this type nat that we're currently defining appears in the definition itself. But that's okay. It's a recursive data type, and we can do that. So let's see if this type checks. Oh, I put a dot there. Wrong language. Okay. Okay, so now we define the natural numbers. And so I guess my point here is that the natural numbers are just a special case of a data type in Pirate. Okay? And I guess what I'm getting to eventually here is that another thing that's not unique to the natural numbers is the principle of induction. Okay, so it turns out, as we will see, that any data type in Pirate, I don't know, perhaps there are some pathological cases that I'm not thinking of, but any data type that you can define in this way will have its own analogous principle of induction that you can use for reasoning about the code that you write that uses the data type. So we're not there yet. But so that's why we're looking at the natural numbers here and looking at induction, because really these ideas that we're looking at generalize to other data structures that we will be using, like lists and trees. Okay, so I thought maybe what we'll do is a little bit of programming with the natural numbers. Okay, so normally you're not programming with the natural numbers because, like I mentioned, they're pretty inefficient. But it's kind of a fun thing to do, and then these ideas generalize to other types. So let's see. Right. Okay. Let me go back to this. Add a new page. Okay. So this time we're going to do something. I want to define a function on the natural numbers. Okay, so we're not going to be doing a proof by induction, but I'm going to be defining a function by recursion on the natural numbers. Okay, so let's say that I want to define addition on our encoding of natural numbers. So we want to be able to, take two numbers and add them together, or say n and m, n plus m. Okay, and so the way that we can define a function for doing computation on natural numbers is actually analogous to doing a proof by induction, okay? But I'll say that I'll define this function by recursion, okay? And recursion and induction are almost indistinguishable. They're sort of the same thing, okay? So, and I'll do it by recursion on the left argument, because we have two natural numbers here. So I'll say, well, let's do recursion on the left. So what that means, we have a base case when that number is 0, okay? So what do you do when n is 0? You have 0 plus m. Well, that would just be m, right? So we'll say 0 plus m is m. And then, for the successor case, the successor of n plus m. Now here, just like before, in the proof, in the inductive case, we had the induction hypothesis. There was something that we kind of had for free that we could use. So there's a similar thing here in the recursive case, is that you can do the recursive call, okay? But it's just like the induction hypothesis, which means you can do it on n, okay? So what that means here is that we have defined already for us, by assumption, n plus m. Okay, that's the recursive call. And then what do you do with n plus m to turn it into the right result? You take the successor. Okay? So here is our recursive definition of addition on natural numbers by recursion on the left argument. And the way that we went about defining this was totally analogous to a proof by induction. Okay? So now we can do this in Pirate. Okay? I'll start a new function. I'll call it, what will I call it? Nat plus, I guess. Okay, it takes m, or n, which is a nat, and m, a nat, produces a nat as the result, and what will we do? Well, so, I wrote this using a very minimalist notation, just a couple equations, but we can translate this directly into Pirate by just doing cases on the left argument. Okay, so this is a very common pattern for doing this kind of function. Okay, so we'll split up the left argument here. It's a nat, and n is the one that we're doing cases on. And now we consider the two cases. We have the base case, and what did we do when the left was 0? Oh, it's just m. M. Okay. And then the other case, when it's s of some, here I have to pick a name, and I don't want to, it's kind of annoying, I don't want to reuse n. That would be, we could do that. I'll just say double n, okay? What do we do in that case? Well, what did we do? We did the recursive call on that sub-natural number, and then took the successor on the outside. So, nat plus and nm, okay? That's the recursive call. And then we'll take the successor of that. Okay? So this kind of thing is fun. You can build up a whole library of operations on natural numbers like this. Once you have plus, you can do multiplication, and you can do exponentiation, and all sorts of stuff. You can build up all of arithmetic using these natural numbers, and it's quite fun. Okay. But, well, how much time do we have? Okay. Right, but so, one of the things that I'm trying to get across is that this is kind of a special case of recursion. that is analogous to induction, right? And so once you get used to thinking in this way, it's actually very easy. That thinking recursively in this way is almost like not thinking at all. You don't really have to think about like what the function does when you run it. You're just kind of, you have some assumption that you can work with. That okay, it's safe to do the recursive call, and then we can just turn it into the result for this case, and we're done. And you don't have to think beyond that. Okay, and so a lot of the time, functions like this end up being really easy, much easier than anything else, once you're kind of used to the idea. Okay. And the same kind of thinking applies to lists, which is what I don't think we'll get to lists today, but probably on Wednesday we'll start looking at lists. So I don't know. So I could start writing more of these functions. That would be kind of fun. Maybe I'll do one more. Okay. Maybe I'll do one more. But yeah, let's do multiplication. Okay? Because it's kind of the same thing. Okay? But let's write it out first. So let's say we want to define n times m, where we already have addition to use. Question?
Yeah, I wasn't sure. What is NN in a function?
That was just a name that I chose because, okay, we can look at this. Right, I guess I probably haven't explained the syntax for cases very much, but what goes here is a pattern that matches the nat. Okay, and of course we have two cases. One is for 0, so when it matches 0, then that case triggers, right? That means that n was 0. In the other case, n was a successor, but when you're a successor, you've got a value inside. Any successor has an inner nat. So here in the pattern, we give a name to bind to that inner nat so that we can refer to it in the case. So I just chose nn as the name. You could choose anything there. You could even choose n, but I don't like doing that because then that shadows the original n, right? We already have something called n, and so if we use n again here, then within this case, there's no way to refer to the original n. Of course, we don't need to in this situation, but it's just confusing when you're reusing the same name for different things. So I don't like doing that. So that's why, yeah.
I've seen 3 different ways to check cases, with the where word, with the check word, and with the cases word.
Okay.
What's the difference?
Okay, so there is a difference. So where and check are used for test cases. So we could, at the end of this function, I could say where, and then I could list some assertions here, right, for tests. And or instead of using a where block, I could say check and put my assertions in here, and that would be the same thing. But those, so for where and check, those are just for unit tests, right? You can just put some assertions there to check that things are right. But cases is something else. Cases is used for doing case analysis on a value or an expression, really. So n here just needs to be an expression of type nat. And so the idea, what happens, well, it'll evaluate this expression to a value of type nat, and then branch on which constructor it is at the head. I don't want to throw out too much terminology, but these cases for the data type are called the constructors of the data type. Okay, I probably should have said that. So one constructor is 0, and the other constructor is s. Okay, so what this means is that it's just like in our inductive definition of the natural numbers, where we had that extremal clause that said, well, these are the only ways you can construct a natural number. Well, that same thing is true here as well, that it's guaranteed by Pirate, that if you've got a value of type nat, there's only two things that it could possibly be. 0 or its successor of something of type nat. Yeah?
Is S a built-in function to Pirate, or is that something that you're defining here?
That is just something that I'm defining here. So yeah, you get to choose the names for the constructors of your data type.
Okay. And so where in this is, I'm not sure if this is a smart question, but where in this is what the successor does? Is that not something you specified? Because
That's a good question. Well, so
as of right now, it's like when you do the case, the second case, it's like what code is running there, like to see if that matches.
okay. So yeah, it's actually an interesting question. So constructors, they don't do anything. Okay, it's kind of like a function that doesn't compute. So let's see, how could I?
Nothing like a constructor in any other language.
No.
Okay.
No, this is just data. You know, it's like if you've got something of type nat, then it's just a little chunk of data, and there are various ways that it could look. It could just be a 0, or it could be s of 0, or it could be s of 0. So if you print it out, that's what it's going to look like. So yeah, the constructors, they don't really, when you can apply a constructor and it just creates a new value with that constructor on the outside. Yeah, but it doesn't do anything.
Okay. That's interesting.
It's a good question though, because you can sort of treat them like functions.
So it's like a modifier to whatever's on the inside.
Yeah, sort of. Yeah. Yeah. Right. So I mean, I could show you here. Sometimes when you're doing this sort of thing, you can define a function like say number 2 nat. Okay, that takes a number and produces a nat, and you would so numbers could be sort of anything, but so I'll just say, okay, if n is less than or equal to 0, then we want the natural number 0, else, oops, what do we want? Something like this. Okay, so the idea is that you kind of, this is not a really pretty definition, because numbers are not as well structured as nats. But still, the idea here is that if n is a number that is like a whole number, or an integer, a positive integer, then this will give you the nat that corresponds to it by just kind of going down to 0 and adding a successor on the way up. So let's go ahead and print this out. Let's say number 2 nat, well, I'll say 0. See what it does? Gives me 0. Okay, let's try 1. Gives me s of 0. 2. S of 0. Okay, 500. And it might just crash. I hope it doesn't crash. Oh boy. Yikes. Okay.
Click stop.
Is there a stop? Oh, there is a stop. Now, okay, if you do this on the command line, I know it'll work. So maybe.
Print 500 S's and then just put 0 in front of them.
Huh?
Is it just going to print 500 S's and put 0 in front of them?
Yeah. Yep. That's. I wonder if it's a type checker, or I don't know what's hanging up here. So let me data nat on nat plus right, we still have time. Okay. So I guess, okay, we don't have as much time as I would like. So what will we do here? I could show you something. So one of the nice things about when you write functions like this by recursion, so you can call this induction recursion. Okay, it is like a special case of recursion where the recursive calls that you do are only on smaller subterms. Okay, so I guess the standard term for this is structural recursion. Okay, where all the recursive calls are on what you would call structurally smaller subterms. Okay, and so when you write your code like this, in some ways it's sort of obvious that it's correct in a way, because you can do a sort of, you can just kind of do a little proof by induction in your head. Okay, that the correctness of the code is apparent from the structure of the recursion that you're doing. So on that note, I can show you something interesting. So suppose that we wanted to prove something about this function. Okay? And there's something, there's all kinds of things that you could prove about it, but there's something that's quite simple that we can look at. So let's look. So never mind about multiplication, I suppose. We have addition here, if you recall. So now, what if I want to show the following? I want to say for all n of type math, the following is true. N plus 0 is equal to n. This should be true, right? And you would think that it would be like immediately obvious. But because the way that we've defined addition is by recursion on the left side, it's not immediately obvious because you just have some n on the left and there's nowhere to go. Right? There's no way to do this. But what you can do is a proof by induction on n. Okay? Because if you recall, induction allows us to prove statements of this form. You say for all n, something is true, some property of n. So let's do the proof by induction. Okay? Base case, 0. Okay, well in this case you've got 0 plus 0 should equal 0. And in this case, we can use one of the defining equations of our operation because now 0 matches on the left. And so this can rewrite, so m is 0. And so this works, okay? Base case is good. Okay, and then the inductive case. Okay, assuming the induction hypothesis, which is that n plus 0 equals n, let us show, keep losing the cursor, here it is, need to show s of n plus 0 equals s of n. Okay, and now again, because this is now s of n on the left, it matches one of these. And so we can rewrite this by this equation. Okay, so where's the cursor? This is equal to s of n plus 0 by that equation. Okay, and then by the induction hypothesis, n plus 0 is equal to n. So we're good. We've got s of n on both sides. And so now we've proved something about addition, a little elementary fact about addition on the natural numbers. But we need an induction to do this. Okay. Okay. So we just have to check if we have a quiz today. That's the last thing. And well, I suppose we'll start talking about lists next time. CS in class. Okay. All right, there's no quiz. See you Wednesday.